Okay, let's try this again. The first recording wasn't quite all that successful, so I'm going to go through, this is the solution sheet, so I'm going to kind of pick and choose some of the ones I feel like you're going to be okay with, and then I'll spend most of the time on the ones that you'll probably need a little more discussion on. Okay, first of all, definition of continuity. Like I said, you will need this for the test, so make sure you're able to define this, especially know these three conditions for sure. And we're saying a point is continuous if the function f of c is defined, if the limit of f of x as x approaches c exists. That means if the left-hand limits and the right-hand limits agree, right? And then if the limit, the limit of f of x as x approaches c is equal to the function evaluated at c, then if all these conditions are met, then we would say it's continuous on the open interval. So let's just look at that. The limit as x approaches 3 from the left. So first of all, here's my function. As x approaches 3 from the left, our y value is -1. Okay, let's look at b. As x approaches 3 from the right, so let's come from the right hand side, our y value is 3, right? So if the left hand limit is -1 and the right hand limit is 3, we say it does not exist. The limit does not exist. Okay, and then a whole separate question, think about back to pre-calculus, what is the function when x is 3, what is y? When the x value is 3, what is y? It's that particular point right there, which is 1. The limit of f of x does not equal f evaluated as x approaches 3. The limit of f of x as x approaches 3 is not the same as the function evaluated at 3, which is this. So that's not true, so therefore this is not continuous. Alright, let's look at another one. Same thing here. Let's look at as x approaches 2 from the left. It's hard to see this one. So x is approaching 2. Our y value is 2. As x approaches 2 from the right hand side, 0. So if the left hand limit and the right hand limit do not match, then the limit of f of x as x approaches 2 does not exist. Now let's evaluate the function when x is equal to 2. And I kind of wrote over that, so you can't see that this one was an open circle, and this one's a closed, but you should have your copy, and you can see that it's the closed circle is there, so because the limit of f of x as x approaches 2 does not equal the same thing as f evaluated at 2, then it is not continuous at x equals 2. Alright. Let me see if I can move this so I can clear the screen. Maybe I can move it over here. Alright. Let's look at number 3. Sorry about that. Okay. The limit as x approaches 4 from the left. Approaching 4, it looks like we're at 1. As x approaches 4 from the right, we're at 1. If the left-hand limit is 1 and the right-hand limit is 1, the limit of g of x as x approaches 4 is 1. Now let's evaluate f at 4. G at 4 in this case, excuse me, we switched to g. G at 4 is 1. Well, if the limit of g of x as x approaches 4 is equal to the same thing as g evaluated at 4, that's what our definition part C of our definition says, then this is continuous. Okay? The same thing on the next one. We're headed towards 0 from the left. From the left, we get 3. Coming from the right, we get 3. If the limit from the left is 3 and the limit from the right at 3, then the limit of g of x as x approaches 0 is just 3. The g evaluated at 0 is 3. And because this value is equal to this value, we say yes, it's continuous. This next part is just talking about different types of discontinuities, and we mentioned discontinuities in our last lecture, but This is continuous at x equals 0. This one is considered a removable discontinuity, and you can see that's an open circle right there. Okay? Another removable discontinuity is if you have an open circle here, but a closed circle on 2 right there. That's a removable discontinuity. And on the algebraic side, if you think back to the last lecture, remember when we would do cancellation and one of the factors in the numerator would cancel one of the factors in the denominator, and we said that was a removable discontinuity? Well, this is what it looks like on a graph. We have a jump discontinuity. That's when we have our functions here with an open circle. Then it jumps there. You can see there's a jump there. So that's called a jump discontinuity. Let me clear that. An infinite discontinuity, it's continuous. And then an oscillating discontinuity here. So those are just some images of some graphs of different types of discontinuity. Now we're going to kind of pick and choose through some of these because I feel like you should be comfortable with this. Let's do this first one. The limit as x approaches 0 from the left. So I'm going along, approaching 0 from the left, I'm at 1. Approaching 0 from the right, and I'm at 1. Well, if the left-hand limit is equal to the right-hand limit, then just the limit of f of x in general is 1. Okay, we move that. Let's do 3. As the limit approaches 1 from the left, so let's head towards 1, and that's 2. Let's approach 1 from the right. Where does that have us at? X approaches 1 from the right, so we pick back up, and oh, that's -1, right? Or is that +1? +1, +1 from the right. Yeah, that's it. +1 from the right, it's at 1. Excuse me. I'm skipping them so I confuse myself for a minute. 1 from the left is -2, 1 from the right is 1. The left-hand limit and the right-hand limit do not match, so the limit does not exist. Okay, so we've talked about that. Let's go down. Let's look at 7. X approaches 0. X approaches 0, just in general. Well, as x approaches 0 from the left, it's this. From the right, it's this. So it's just going to be 1. So number 7 is 1. What is the function evaluated at 0? Well, that's also 1. And by definition of continuity, we said if the limit of f of x as x approaches 0 is equal to the f evaluated at 0, hence they're the same, then we would say, yes, it's continuous at 0. So this is kind of where you're going with the rest of these. So I'm going to encourage you to just finish those out and look at the solution sheet to work with the rest of them. They're all very much similar in that nature. Okay, and we did this in class too. Which points are continuous? Well, what we did in class was find the discontinuities, which, remember, it's discontinuous when the denominator will become 0, so we find out it's discontinuous at x equals 3. Well, this is what we did in class. Today, all we do is now we say, where is it continuous? So basically, we would say everywhere else, right? So we would say from -infinity to -3, parenthesis, union. This is interval notation, so we just want to take it one step further and say, well, where is it continuous? Number 2 is very much like that one. Let's see. Number 3, factor the bottom. There are no removable discontinuities, so it's discontinuous at 5 and -4. Just take a minute to recall the interval notation on that. This is one of our special ones, remember that. Oh, this discontinuous when the denominator is equal to 0, so it's continuous everywhere else, right? And 6. Same thing, okay? First of all, we would get indeterminate form on this one, but we would factor. This is called a removable discontinuity, right? So the only one that's left is the discontinuity at x plus 5. Well, it says define f evaluated at 2 for the given function so that it's continuous at x equals 2. So we take the removable discontinuity out and then we substitute in f at 2. So plug in a 2 right here and you would get 2 plus 5. So f of 2 is just equal to 7. Okay, so that should be pretty comfortable for you.